Welcome back. All right, let's see what we got in the room here. We got everybody. Right on. I have to check that from time to time, administratively speaking. All right. Now, topic C, network protocols and stuff. So the goal, we're going to identify threats and targets potentially, how those threats will impact your network, and take a look at securing our network by layers. And first, we got to kind of understand those layers a little bit. Okay, well, there's a short blurb in here, it's not that short actually, about the OSI model. And there's not a tremendous amount of information on the test about it, but it does expand upon the original TCP/IP model we talked about before with its 4 layers, right? The application layer, the transport layer, the internet layer, and the data services layer. The OSI model is 7 layers, 7-layer OSI model. Not a big deal on the Security Plus exam. It is on the Network Plus exam, but you've got these 7 layers, and basically what these layers are, it's a conceptual framework. It's a model for seeing how the various network protocols interact with each other. One thing leads to the next, and so on. You've got your at the bottom of said protocol model, you've got the physical layer, and that's the actual wiring and protocols associated with moving electricity through these cables and such. You've got certain devices that tend to be known as physical layer devices, things like hubs and repeaters, those devices that just electrically rebuild the signal so it can continue moving down the wire. Your network adapter to some degree, pretty much anything that's actual physical in nature, things that you plug something into or things that are plugged into themselves and whatever. The next layer up, the data link layer, that's concerned with physical addressing, primarily the MAC address, but that's not the only layer 2 address, but that level. Devices that operate at the data link layer are your switches, because the switch will maintain a list of MAC addresses. That's how it can forward traffic efficiently and effectively. There's a device called a bridge, which is essentially a device that predates the switch, and its primary job is to kind of segment the network into a couple of network segments, and traffic from one segment didn't need to slop over into the other segment. And now again, the switch implements that same technology at the port level, through hardware. So again, we maintain a full MAC address list on the device so it can forward traffic as necessary. Your NIC is a layer 2 device because it's it's all about that MAC address. Moving up to the network layer, you've got that's where IP comes in. And that's where we handle things like a routing. Use our IP address for routing purposes. And if there's a device that operates at layer 3, that would be the router. And of course, your routing protocols operate at that layer because that's where routing takes place. Your layer 4 is your transport layer. And the 2 primary transport layer protocols being TCP, Transmission Control Protocol. That's the one you would use if you need guaranteed delivery, error correction, sequencing, all of that stuff. And as you would imagine, there's some overhead associated with that. And then there's UDP, or User Datagram Protocol. That's where you don't need any of those special fancy features. You just need an entry point to the network, and off you go, kind of a thing. So a couple different transport layer protocols. They do mention a new one in the book here, Stream Control Transmission Protocol, SCTP, which combines TCP and UDP into one protocol. I would need to research that one in more detail to really understand what it's doing. That's they just kind of sprung it on us there. And then you move up into the application layer stuff. The session layer is used to identify that this particular packet belongs to a specific communication event, because you may be connected to a specific machine and have several different things going on. That machine may be a web server, maybe an FTP server, maybe an email server, but it's all on the same physical machine. So I need to be able to identify that this packet belongs to this email session or this web session potentially. Above that is the presentation layer. The presentation layer takes your raw data and transforms it in some way. And one of the more common transformations would be encryption. If my data needs to be encrypted for transmission over the internet, that job is handled by the presentation layer. And then finally, at the top of the stack is your application layer, where those are the network applications that actually let us do our job. Our HTTPs and our FTPs and DNSs and those kind of things. There's lots and lots and lots of network protocols. But the point is, the raw data comes out of some application at this layer, and that raw data is of interest to some application on some remote machine. Everything else is packaging and delivery. So, and they all sort of interact with each other in this sort of hierarchical structure, and that's what this OSI model does, is it places the different network functions in the proper sequence into how they interact with each other. Okay. So then let's move into talking about some TCP-related things, TCP/IP related things. We talked about the protocol suite before, the concept of it being a non-proprietary. In other words, it doesn't belong to any particular vendor. Allows us to communicate across multiple vendors' different products because they all implement TCP/IP in a way that enables that interoperability. AppleTalk did not make the cut, sadly, because well, it's AppleTalk, and also the World Wide Web Publishing Protocol kind of tipped the scales in favor of TCP/IP. So it is what it is. Notice, if you will, there's a couple different versions of IP. The version we currently use, the 32-bit address version, is IPv4. And it's, again, it kind of goes into a little bit of explanation about, what those address components are all about. And it's a kind of a nonsensical discussion of bytes and bits and, ones and zeros. It's kind of meaningless and nonsensical. Again, we're really not going to get into the concept of the address and the subnet mask to define, okay, how much of the address is the network part and how much of the address is the host part. All those are very important. And then IPv6, the follow-on, yes, for those of you that are wondering, there is indeed an IPv5. That was a 64-bit addressing scheme, which was designed to handle the specific requirements for streaming video, but kind of at the same time, the developers of what came to be known as IPv6 doubled the space, 128 bits, and already handled the video part, but did so much more that IPv5 was never implemented. We just went right to IPv6. If you take a look in the book, you'll see that IPv6 looks just a little bit different. It's a 128-bit addressing scheme, but instead of using decimal representations like IPv4 does, it uses hexadecimal, base 16. And in base 16, the legal values are 0 through 9, and then A, B, C, D, E, and F. A representing the decimal value 10, B representing 11, C representing 12, and so on, F representing 15. You include 0 in there, and there's 16 unique values that can be displayed with a single hex character. So if you look at a IPv6 address, what you have 8 groups of 4 hex digits per group, and 4 hex digits. Each hex digit is 4, and 4 of those, that's 16. So basically each group represents 16 bits. There's 8 groups, so 16 times 8 conveniently is 128. And and you'll see those groups, they'll be separated by colons. And you may see a situation on the test where you have to identify an actual legitimate IPv6 address. That's about the level of depth you can be expected to see on this particular exam. It goes into a little bit of detail, but again, not enough to warrant worrying about. DHCP, Dynamic Host Configuration Protocol. The object there being, hey, this is a service that automatically assigns you an IP address. Because in IPv4, when you turn the machine on. It doesn't have an address. It has to obtain one, either manually, you have to manually assign it, or you configure that machine to obtain its address automatically through DHCP. And then DHCP provides the address for the host. So it's a pretty important service. And DHCP has a secondary function. Once the address is assigned, DHCP can then register you with DNS. Make sure your address is now in the DNS database also. So DHCP pretty handy. Now IPv6, one of the benefits of IPv6 is you automatically, upon startup, generate what's known as a link local address, a fully functional IPv6 address that lets you communicate on your local network without asking DHCP to give you an address. So you're thinking, well, that's great, but we still use DHCP in v6 because we need a public address. We still need to generate an address that'll let us get out on the internet. And even though you can configure IPv6 clients to kind of auto generate their own public address, we tend to let DHCP do that because DHCP does a variety of other useful things, such as also assign the default gateway address, also assign DNS server addresses, and there are other activities as well. So DHCP has a valid function both in v4 and v6. And before we get into DNS here, you'll also notice in the book, in the same place, there's a few terms such as IEEE. You've probably heard the term IEEE before. That's the Institute of Electrical and Electronics Engineers. They're a standards body, and a variety of network standards, computer standards, are defined by IEEE, so you'll encounter them. You see the term APIPA, Automatic Private IP Addressing. In an IPv4 network, if you're configured to obtain an address via DHCP, and for some reason you can't do that, you'll wind up getting what's known as an APIPA address, or a 169.254 address. That's a specific address range that's kind of actually sort of donated by Microsoft as part of their address range specifically for this purpose. And an APIPA address is a lot like a v6, a link local address. I can communicate on my local subnet. I can't. It's not routable. I can't use that address to take me to another network. So you're stuck, and there's nothing you can do with that. You have to obtain a legitimate address if you want to go out on the internet, kind of thing. But at least if you pick up an APIPA address, you can talk to those other guys on your local subnet. And again, the thing to remember is, if you see the address range 169.254, that's an APIPA address. And if your problem is, hey, I can't get to the internet, and you look and see I've got an APIPA address, well, that's why. Or I've got a perfectly valid DHCP server, but I still got this APIPA address. What's going on? Then you look and see that you either are missing your default gateway address, so you can actually get to the DHCP server, or whatever. So, but it's an indication that the fact that you got a 169.254 address in the first place means something is wrong in DHCPville. For some reason DHCP did not provide you an address. Okay. DNS, a domain name system. So a little background. The internet sort of came to be around 1992-93 timeframe. Now, prior to the internet, if you wanted to be able to communicate using a name like www.microsoft.com, for example, instead of communicating via IP address, you could do that because your local machine, there was a file on your local machine called the hosts file, HOSTS, hosts file. And what this host file had was a one-to-one matchup between an IP address and a name. So when you were communicating with somebody on the network using that name, your system, your computer would resolve that name to that specific address based on the host file. Okay, well, that was great for a pretty small local network, but once the internet kind of became a thing, that would not really work anymore. That would not really work anymore. So this DNS infrastructure, which consists of hundreds of name servers scattered throughout the world, hosted in government facilities and private industry and so on. They're everywhere. The job of DNS is to resolve names to IP addresses, which used to be the job of the hosts file. The host file obviously is not kind of a scalable thing, so you needed an infrastructure in place to perform this task for us. So that's where DNS came from. That's the function of DNS, is to allow us to be lazy and use names when we really should be using IP addresses, but we don't, that's not how we roll. So that's not what we're going to do. We're going to let DNS resolve that name to the IP address, return the IP address to us, so that we can then place the IP address in the IP header so that my packet can leave the building and get delivered wherever it needs to go. Okay, so and conveniently DNS kind of came online just about right at the same time, right about the same time that the internet came online. Coincidence? I don't think so. Before we leave DNS, in the book it talks about, hey, since DNS is kind of a big deal, DNS is it's pretty much required by the infrastructure for us to kind of communicate in public networks. So DNS would be an obvious target for the bad guys to disrupt your network communications and so on. So there are, so that's a special device that needs special, handling from a security perspective. A whole list of bullets there. You don't want your DNS server just sitting out on the internet. You put it behind a firewall in a DMZ, and you want to make sure that DNS server in the DMZ only exposes your public addresses and doesn't expose your internal address space to your internet crowd. That would be bad. Set firewall rules to prevent unnecessary traffic from even getting to your DNS server. Only expose, again, hardening. Only expose the ports that are necessary for this function to work properly. DHC filtering, filtering out machines that you don't want to be picking up DHCP addresses, because then they would be registered with DNS incorrectly. So you want to ensure DHCP is properly configured as well. Since all of this ultimately is software, there's the possibility, the very real, almost certain possibility of buffer overflow exploits. So you want to ensure that your DNS software is pretty clean and has been properly vetted and so on, because buffer overflow errors lead to potential problems. Using SSL, basically, you can configure DNS to only accept secure communications and not just accept entries from anybody that just comes along, like Microsoft Active Directory. Lets you there's a mode that allows you to only process secure updates, which means, hey, I'm only going to add records to my DNS database from other users that are in my DNS namespace. I won't accept information from people outside of that. And keep your DNS updated. There's patches and updates to DNS just like any other piece of software. And back the database up. It's backed up by default, about once an hour kind of a thing, but you want to manage that so that if something goes bad, you can recover your DNS data and continue operating functionally and so on. So again, DNS is a one of those critical infrastructure items that is worth extra consideration from a security perspective. HTTP, as you know, is pretty much the primary way we do business these days. A lot of things we do is over the internet, or if not the internet, we use HTTP services on the intranet, within our own organization. There's, we have internal web servers, and State Department, we've got, SharePoint services and a variety of other things as well. So web server, HTTP, web server security is a big deal. So there's several specific items you want to look at there. Again, a dedicated web server should be hardened appropriately to, block ports that are not in use, and only run things that need to be running. Other services should be disabled and run on the appropriate machines. Avoid remote access to web servers. Now, there's technology has come a long way, and now you, the administrator, you've got the ability to connect remotely to that web server, create an administrative connection so that you can administer said web server, and you should not do that. You should disable that capability. And you're thinking, what? Why would I do that? Because that's, that sounds good. I can be at home and I can access it from home. And see, the problem is if you can access it, the bad guys can access it. It may be a little harder for them to do and take them a little longer to gain access, but ultimately they can, and boom, it's game over. So you should generally disable that remote access and require the administrator to actually touch the physical machine in order to make changes to that server. It's inconvenient, but ultimately it's safer. There's when you install your web server, there's a predefined set of folders that are created and so on. There's in Microsoft environment, there's the inet pub folder, and then there's the www folder underneath that where the web server files are stored. And then by default, it's on the C drive of your web server. Well, everybody knows that, and that's bad. If everybody knows where the goods are, it's a kind of a target-rich environment there. So when you install your web server, it's probably good to actually put those files literally somewhere else, another drive, a secure drive, a safe drive, that's not right there on your operating system drive. So you should take advantage of those features. Install your patches and updates. Delete and disable unused user accounts are the devil's playground. State Department, those guys, man, they're awfully twitchy about unused user accounts. If you've got a user account that there's no carbon-based life form directly attached to, that thing's got to go, which is good for security, because an unmonitored user account that can be pretty much the identity of which can be assumed by anybody, that kind of defeats auditing and allows users to access things that they themselves wouldn't have access to. So unassigned user accounts really should not be used anyway. And State Department, they pretty much enforce that, which is good. Use various security tools. I mean, there's a variety of ways to secure web servers, and take full advantage of those. And then do continuous monitoring. Scan your servers looking for ports that are open that shouldn't be, and other vulnerabilities that may have crept into your scenario there. Again, like a DNS server, a web server requires a little bit of an enhanced monitoring posture, just because it's so visible and has so much direct impact on your users. To assist you is SSL, the Secure Sockets Layer process. This is a process that was invented / popularized. You guys remember Netscape? The old web browser platform back in the early days of web browsing. They invented this SSL process. And here's kind of how it works. And remember our discussion of cryptography. That'll come in handy right about now. So you've got a web server and a web browser. The web server's on the right, web browser's on the left. So you go to some public, HTTP site on the, some vendor's website. So you're buying stuff, you're throwing stuff in your shopping cart. You're about ready to check out. So you hit the Go to Checkout button. When you do that, what happens is that's step one. That's a request secure connection, because what you're doing is you're saying, hey, I want to go to the HTTPS server. Well, when you do that, what happens then is the web server will send you his certificate, the web server certificate that he obtained from some trusted third party with the intention of being able to sell you stuff. Because, you know, if the web server gives you a certificate that is issued by somebody that you trust, well, then that trust will extend back to that web server. So the web server sends you his certificate. His certificate contains that public key. So now you have the web server's public key. Only the web server has the web server's private key, right? Okay, so you have the web server's public key. The step 3, negotiate encryption. The two of you work out some basic parameters, and then the next step, which isn't listed here, the client, the web browser, you generate a symmetric key, you know, for bulk encryption. You're going to use that symmetric key to encrypt your data, and that data would include things like your credit card number, you know, the order details and such, because you don't want to send your credit card number across the sewer of human communication in plain text, would you? Say, no, we would not want to do that. So you generate a symmetric key that you then use to encrypt the data. You then use the web server's public key to encrypt your symmetric key that you just created yourself. You attach that to the message, away it goes. All the internet scumbags bounce off because they don't have the web server's, you know, the corresponding private key. The web server, on the other hand, does have the private key. The web server uses his private key to decrypt your session key. So now both of you have the data decryption key, encryption-decryption key, and boom, that's the key that the two of you will now use throughout this session. So SSL and its follow-on TLS use a combination of symmetric encryption for bulk data and asymmetric encryption for encrypting those keys. And that process stood the test of time, works good, lasts a long time. Again, TLS is an enhancement of SSL, and ultimately your web servers, your vendors are going to move to TLS, and you kind of leave SSL behind. It's going to be a gradual thing. If you go into your web browser properties and go to the security tab, you'll see there's several checkboxes for SSL version 1, version 2, version 3, and then there's TLS, version 1, kind of a thing. And you'll probably see, a couple of the SSL versions and the TLS version checked. So when the web server does shift to TLS, you're already equipped to handle it. There's no obvious difference. There's nothing new and exciting you have to do. It's going to be transparent to the users. So eventually, SSL will stop being used, and TLS will take over for it. Like I say, it's compatible, but it's enhanced. There's some additional things that TLS does that SSL does not do. But definitely recognize that SSL and TLS are essentially the same process, with enhancements. Okay, again, that process is how we perform e-commerce to this day. And that's implemented in our HTTP protocol in something called HTTPS, Hypertext Transfer Protocol Secure. And HTTPS uses port 443. So when you hit that go to checkout button, you're basically saying, hey, I'm going to talk to you on port 443. And the web server is, of course, listening to you on port 443 for secure communications. Then they do the SSL negotiation and work that stuff out, and then the data gets transferred. So no insecure data gets transferred over the internet, because that's bad, and we don't want to do that. Okay. Now, another internet protocol, something called SSH, Secure Shell. It may be important to know that SSH uses port 22. Port 22. It's probably not. It would be on the Network Plus test. It might be on the Security Plus test. But the concept here is SSH is a certificate-based, secure protocol for communication sessions. SSH has pretty much replaced Telnet. As Telnet is one of the granddaddy protocols of the internet, and that would be used to create a remote connection so I can connect terminal style to your machine and issue commands to it and so on. Well, that was insecure because Telnet sends its password in plain text. SSH doesn't do that. It encrypts the entire session. All the data in there is completely safe. And SSH is pretty much not replaced, but your file transfer protocol, there's several of those. There are now SSH-enabled versions of FTP, like FTP-S, for example. But again, SSH port 22 is a certificate-based, public key infrastructure-based security protocol. Okay. Some more TCP/IP stuff. SNMP, Simple Network Management Protocol. SNMP uses port 161, probably useful. Another thing that's useful about SNMP is this has been around since the dawn of the internet, basically, SNMP, and it's a management protocol, and it involves you, the administrator, installing what are known as SNMP agents on what are known as managed devices, servers, routers, printers, other devices. Now, these agents will read and write the data to something called a MIB, M-I-B, Management Information Database. And there are different, very specific MIBs for very specific devices. The server MIB looks different than a router MIB, looks different than a printer MIB. And these SNMP agents read and write that data. And you, back at the office here, on your SNMP management console, you can retrieve data from a remote device's MIB. There's a SNMP GET request to allow you to retrieve data from that MIB. There's SNMP SET requests to let you write data to the MIB. But the most fun thing you got going here is when you configure your managed devices, you can set what are known as SNMP traps. An SNMP trap is where you have identified a specific performance factor or specific, value that when a particular, threshold is exceeded, you want to be notified. So basically, it's like an unsolicited GET request. So you're sitting there minding your own business, and then some server says, process utilization hit 91%. Something like that. Maybe you want to be notified when it went over 90%. So now it's like, oh, I've got this piece of information I can now act on, and it gave it to me automatically based on conditions I was interested in knowing about when they happen. So these SNMP traps enable your managed devices to kind of respond when that condition exists. Very exciting. Oh, the thing I wanted to point out, there have been several versions of SNMP over the years, and it's not until we got to SNMP version 3. SNMP v3 is the first SNMP version considered secure. Why? It's certificate-based. It provides encryption services and authentication services, whereas the previous versions of SNMP really did not do that. So just as a quick and dirty, just remember if it's asked you which version of SNMP is generally considered secure, that would be version 3. Okay, and that's testable, believe me. All right, more TCP/IP services. We talked about ICMP before, Internet Control Message Protocol. ICMP is used by ping and traceroute to determine connectivity. This is an example of ICMP in one of its functions in a TCP connection. This is basically a method of flow control, and what's going on here is you got your sender, you got your receiver. your receiver has a buffer, a receive buffer. This says router buffer, but really it's a receive buffer on the receiver. It's an area of memory. And as my data is coming from the source, the receiver may or may not be able to handle it in real time because, he's busy. He's doing stuff. So the data goes into the buffer to be processed, when I get around to it. Now the deal is, if my buffer fills all the way up, imagine, if you will, I've got a glass, and it's completely filled to the absolute very top with beer. All right, I'm trying to make it realistic here. The next drop of beer that goes in that glass, where's it going to go? Over the side. Why? Because the beer glass is full. So that's bad. We don't with data. We want to try to avoid losing traffic, losing packets, because with TCP, guaranteed delivery, right? So at some point there's a trigger. Think of it as a float switch. So when that float switch activates, it's like on your toilet. When your toilet tank fills up with water, it activates this float switch, which turns off the water. It's kind of the same deal. So the float switch activates, and then ICMP sends out what's called an ICMP source quench message and says, stop sending data. Stop. I'll tell you when it's okay to send me more data. So the sender stops sending data. The buffer has not overflowed. The receiver then turns his attention to the receive buffer and starts processing the packets that have arrived in there. My buffer goes down, my toilet tank drains, and then at some point ICMP says, all right, start sending me data again, and then the process continues. So again, ICMP, the magic keyword there is M, messaging. He's kind of provides the eyes and ears to TCP. To IP, because IP's busy, routing packets all day. That's all he does. That's all IP does. It's his helpers like ICMP that operate behind the scenes and take care of all the administrative details. So ICMP, very handy. There's a little something called IP security, IPsec, and this is a protocol that's widely used. It's non-proprietary, so it can be used in a variety of environments, and it provides data security in transit. This isn't useful for storage. You do something like BitLocker, to encrypt the hard drive. But when your data is moving, it provides security. What kind of security? Provides encryption, provides authentication, provides anti-replay protection, due to the way it deals with sequence numbers and things, provides non-repudiation services, all of that stuff. The eavesdropping and sniffing protection, well, there's nothing to prevent you from, eavesdropping, from capturing those packets or retrieving those packets wirelessly, whatever. There's nothing to prevent you from doing that. But you've captured a bunch of gibberish that you can't read because it's encrypted. So it doesn't stop you from somehow being able to, to capture the packet, but it does stop you from being able to read the contents of the packet. So again, there's a variety of IPsec standards that are negotiated between the two parties that are communicating, having to do with which encryption algorithm am I going to use, what are my key sizes, how often do I rotate my keys, what authentication algorithm am I going to use, blah, blah, blah. All these things they negotiate, and then all further communications between those two hosts are configured as IPsec has been set up for them to communicate. Pretty handy stuff. I for Internet, and SCSI. SCSI is it stands for Small Computer Systems Interface. It's it's kind of got its start back in the old Unix days, and it's for hard drives and other sorts of devices, storage devices. Well, basically, we've got, iSCSI is a protocol that enables storage networks, kind of SANs, to communicate over the internet, which is, suboptimal. I mean, in a perfect world, all the traffic going back and forth within a storage area network is operating on this what's known as fiber channel connection, fiber optic cabling, and it's operating at these super high speeds and whatever. But if I need to leverage my data storage capability, if I need to, use my storage area network and all I got going for me is the internet, iSCSI is a way to, to leverage access to my storage areas, my storage area networks using internet technology. So that's what iSCSI is all about. Again, is that perfect? No, but if I don't have the other infrastructure in place, it's the best I can do. So that's its specific function. In fact, in the book here, they mentioned fiber channel, and fiber channel. Notice the odd spelling of fiber channel. Instead of like F-I-B-E-R, like I would spell it, that uses the kind of old school, British style spelling to kind of remind us that we're not, this fiber channel architecture is not strictly limited to fiber optics. There are some copper-based media that can be used with fiber channel, but the concept being, I've got my file servers that connect to my storage area network via fiber channel infrastructure. There's all my data storage is over there that my various servers can get to at high speeds and so on. So again, fiber channel is sort of the primary protocol that storage area networks are built on. iSCSI is like your second choice because you're accessing them over the internet, not over the direct fiber channel infrastructure specifically. There's something called fiber channel over Ethernet, which lets you use fiber channel protocols over the Ethernet networks are generally high-speed networks, but you have to adapt the protocols so the one's compatible with the other. So there is fiber channel over Ethernet, and a little blurb in the book you should probably read at some point. But again, just recognize that FCOE is fiber channel over Ethernet to enable us to leverage some existing technology with our storage networks. The granddaddy of all network protocols is Telnet, and allows us to create a remote connection to somebody so that we can interact with them. And again, the issue there is the password is transmitted in plain text. Our man in the middle, bad guy here, can simply sniff the password right off the network, and that's bad, as you might guess. So Telnet, which uses port 23 by default, by the way, Telnet, port 23, has been largely replaced by SSH, which defeats these man-in-the-middle attacks. So this is good. Again, we still use Telnet to some degree in certain low-security environments, but we're getting away from using Telnet. Oh, here's a blast from the past. NetBIOS, Network Basic Input-Output System. It's really an application programming interface is what it is. And back in the early days of networking, a lot of our applications that we use to this day are NetBIOS based applications. Again, this predates TCP/IP. So applications communicating across networks pre-TCP/IP were use NetBIOS to communicate, manage the connection between the users, and connectionless in much the same way IP is connectionless or UDP is connectionless. Performs a variety of services, but it's a couple things you're going to want to do. You're going to want to disallow root access, which basically is the lowest level of access, meaning the highest level of access. And if you're accessing stuff at root level, there's pretty much nothing to stop you from accessing pretty much anything at any level. A null session is basically where you're able to connect without providing pretty much any credentials at all, more of kind of like an anonymous connection. And that's sort of built into NetBIOS, but that's an obvious way to get yourself into trouble there. So, but the deal is NetBIOS predates TCP/IP, but we haven't eliminated it altogether. Someday we will, but we haven't yet. So there's a protocol called NetBT, Net Bias over TCP/IP. So essentially, you can use your TCP/IP infrastructure and interact with net bias related things. Yeah, there you go. But net bias related things using your TCP/IP infrastructure to access that stuff. So again, there's certain applications, like for example, when you go to the network icon and you say, like view workgroup computers, and you like see a list of computers pop up, that's basically a net bias application that displays to you your local network computers on the screen. And again, someday that'll be modified and changed, but it hasn't been yet. So yeah, whatever. So just kind of be aware of that. Again, be aware it's kind of a separate API, application programming interface, but it's been kind of sort of accepted within the TCP/IP umbrella for management purposes. File transfer is a pretty important thing. I mean, between Telnet and FTP, that pretty much covered everything we really needed to do with networks back in the day. We needed to make connections to remote machines and talk to them and stuff, and we need to be able to move files around. Well, in the early days, we had FTP, and FTP's File Transfer Protocol, and FTP uses ports 20 and 21. Port 21 for I'm listening for an FTP request on port 21. And port 20 is the port FTP uses to actually make the connection for sending the data. So there's FTP. Then there's an old obsolete file transfer protocol called Simple File Transfer Protocol, SFTP. It's nobody uses that anymore. There's a UDP file transfer protocol called TFTP, Trivial File Transfer Protocol. Used to be you needed to know that FTP used port 69. So write that down. Now TFTP is basically UDP based. Now when you're thinking file transfers, you're thinking maybe large files, and you're thinking, well, I kind of really think I need that guaranteed delivery, and I need acknowledgement, I need sequencing, I need all that stuff. You generally do. There are certain circumstances though where TFTP is the right thing. An example: you've got a Cisco router, or several routers. You're in your router room, and there's the actual image, the IOS, the Internet Working Operating System, basically the Cisco device operating system image. It's corrupt, or it's missing, or something's wrong, and your device can't initialize. So in the config file, you may have it configured to go to a TFTP server, which would be right there in the server room with you, and retrieve the image from a TFTP server. So effectively, it's a UDP stream, and either everything has to complete successfully, or you have to start over, which would be murder in an environment like the internet. But in a kind of isolated environment like a server closet, a router room or something, there's nobody else is connected directly between the router and the TFTP server. So it's a very low overhead, way to deliver packets. Everything goes, one packet at a time in a continuous stream. They get delivered, and so it works great. So TFTP, even though it's UDP, is still widely used in these. Well, here's another reason. My Cisco router that is lacking an operating system image has just enough brain power to go to the TFTP server. Remember, he doesn't even have an operating system set up yet. How in the world is my brain dead, not even a router yet? How's he going to even create a TCP session? He does not have the ability to even do that. So that UDP connection is really his only option. So combine that with the fact that it's on an isolated network segment where there's no other traffic, which means generally that TFTP connection is going to be successful. So it's a very, very important file transfer protocol. It's just not one that most people consider because it's not internet friendly or anything. Okay, there's an SSH enabled version of FTP. It's actually you'll see it referred to as SFTP. Now, clearly that's confusing because there's an older protocol called Simple File Transfer Protocol called SFTP, But that one's obsolete, and the any reference these days to SFTP would be the SSH-enabled version of FTP. Now, look at the bottom of this list. See FTP-S? Well, that's an SSL-enabled version of FTP. SCP, that's a Unix protocol. There's a variety of Unix protocols. There's a protocol called RCP, Remote Copy Protocol. Well, this SCP, Secure Copy Protocol, is the SSH-enabled version of RCP, for the Unix folks. So again, a variety of file transfer protocols, and given the choice, for, obviously other than a special purpose thing like TFTP, given the choice, if you have the ability to use SSH, that would be better. That would be preferred, in fact. Remember our previous discussion about port numbers. There's, in the network world, a port is a logical endpoint between two communicating parties there. And we, there's 16 bits in play, and 2 to the 16th power is 65,536. So there's that many port numbers. So there's 3 separate blocks. There's the well-known ports from 0 to 1023. There's the registered ports from 1024 to 49,151. And then 49,152 to 65,535 are our dynamic ports. So well-known ports, all of the protocols that we've been using for years have numbers in that range. Like port 80, port 23, 22, 21. 25. So there's, so these guys, the standard bread and butter network applications that have been household words for the last 20 years, those guys have assignments down in that well-known ports range. Well, there are thousands of network protocols, thousands of them. So the rest of those guys all have port assignments in the registered ports range, and then the dynamic ports are available to whoever needs them. If I'm a file transfer protocol, I might grab me a couple of those dynamic ports to facilitate the file transfer, and then when the file transfer is done, I release the ports and somebody else can use them. Kind of a deal. Okay, there's a nice list. It's a short list, but a nice list of common ports. Again, although this test really doesn't looks familiar. Oh, okay, yeah, that's leet speak. Anyway, there's a nice list of port numbers. Is there a slide for that? There's not. So in the book, you'll have to kind of look those over. Again, that's not the only ports that are important in the world, but again, the Security Plus test really doesn't beat you up on those too badly. But that's a fairly good, kind of core group of ports to just understand, to recognize. All right. That's the end of this topic. So there's an activity associated with that. Installing a web server on Server 2012 and configuring it. That's useful and fun. What else is useful and fun is me to be able to get to the next section here so we can keep going. Let us stand by. Another IPsec exercise in there. Do that one as well. Kind of show you how to set up your IPsec properties on a Microsoft system, which is representative. Okay. And that takes us to topic D, Secure Network Administration Principles. Stand by while I check something here. Back. Very weird. Okay. That didn't help at all. Well, never mind. Okay. Oh, great. I hate having to troubleshoot readers. So annoying. All right, topic D. Here we go. All right, and we'll finish this up, and then we'll probably go grab some lunch. It's only 6 after. I'm probably want to run you guys till 11:30 or so, or whatever, something 30. I want to run you guys to something 30, and then break it for lunch. But let's look first of all at some secure administration principles. Rule-based management, right? Use of rules. Who do we know that operates with rules? Firewalls. Basically, we've got a set of rules that are in place, and then it's automatic. The packets come up to the firewall. They're compared against the various rules. The first one that applies, the first one that matches applies. Boom, you do what it says. Easy. And again, these rules, again, that's just an example, but there's several other rule-based examples here, as we'll see. Take a look at these network administration security methods. Okay, and we'll talk about some of these. Now, top of the list, a flood guard. As we've discussed, a large percentage of your network attacks are flooding type attacks. Well, a flood guard is a tool, hardware, software, tool that is configured to identify specific types of flooding attacks and then do something about it. Includes, it's like a specialized intrusion detection sensor, one that identifies the specific type of flood attack is underway, and then takes measures to prevent that from happening. Okay, so flood guard, just what it sounds like. I mean, since network attacks, a lot of them are flood type attacks. A flood guard is a countermeasure in the form of an intrusion detection system sort of deal that identifies a flood attack and takes appropriate steps. Let's talk about loops. Loops are bad. In a network environment, let's start up at layer 3. Let's start up at the where IP is. The goal of your routing environment is to configure the route table on each router to where it has the best information to how to get to that remote network the quickest. So if these routing protocols are properly configured, that takes care of itself. A misconfigured routing protocol, or heaven forbid, you're doing all that stuff manually, if you misconfigure that and have router A point to router B as the next path, and router B points back to router A to get to the same place, that's what's called a routing loop. This is bad. Your packets are going to ping pong back and forth between them until they expire and they'll get dropped. So at layer 3, your loop protection is provided by your routing protocols. Now let's talk about layer 2, the data link layer, where we're dealing with MAC addresses. Due to certain behaviors in a layer 2 environment, if you have an actual physical connection that is an actual like loop, like you got like 2 or 3 switches in the network for redundancy, but somehow you've got a physical connection between those switches in a loop configuration, that's bad. Certain types of traffic, broadcast traffic, will never stop. It will pass around that loop, between those switches forever, thus inhibiting other traffic from using those traffic paths effectively. So a loop at layer 2 is bad. And a loop at layer 2 is handled by something called, write this down, STP, Spanning Tree Protocol. Spanning Tree Protocol, the job of Spanning Tree is to break loops at layer 2, at the switch level. So that basically there's all the switches get together. There's this election process based on some stuff, and at the end of this election process, somebody's elected the leader, and then the various links are prioritized, and then it's like a game of musical chairs. At the end of the day, some poor guy doesn't get to sit down, and his link is disabled, thus disabling the loop. So the spanning tree protocol was invented pretty much for the purpose of eliminating layer 2 loops, and it's standard, kind of built in, has to be available to prevent this sort of thing. So at layer 3 in the routing world, your routing protocols are going to eliminate routing loops. Switching loops are eliminated by something called STP, Spanning Tree Protocol. All right. Port security. Okay, well, at the port level, you're generally talking about the switch again, and the switch, basically, he's all about that MAC address. So port security involves how you manage the traffic going across that switch, and basically a lot of that is MAC address based. Of course, proper configuration, you harden the device, right? You turn off unnecessary things. Any ports, and we're talking about physical ports, any ports that you're not currently using, shut them down. We don't want some bad guy to be able to sneak into the back of our office complex there and find an open network port, and he plugs in and he's retrieving traffic from my network. That's bad. We want that port to be shut down so he doesn't have that capability. And if you're moving people around and somebody needs that port to be open, you open it up. Pretty straightforward. Applying patches and updates, hiding responses from ports indicate their status, allowing access of pre-configured connections only. What does that mean? Have you ever, just try this on your own, just at some point, and this kind of reflects that. If you go on your web browser and you go to CNN.com, you will go to CNN's website, and you'll see the news, and you'll see that it's current, and you'll see the date, time, and all that other stuff, telling you, yep, I'm connected to CNN.com's web server. Okay, once you're satisfied that you're actually at CNN, then go to your command prompt and type ping CNN.com and see what happens. I'll tell you what happens. You're not going to get a response. You know it's there. You just saw it. You just verified that CNN is up and it's operating, but it doesn't respond to your ping. Why? Because it doesn't want to. It's I discovered a long time ago. I was doing some class and we were analyzing traffic, and against our network that was like attack traffic. It wasn't very powerful attack traffic, but what it was. The majority of malicious or unknown traffic or unwanted traffic was originating from a South Korean middle school. And basically it's kids in the computer lab screwing around. And there was a whole bunch of, pings and other sorts of things coming from the South Korean middle school that was kind of annoying. So, we blocked them and whatever. But, it doesn't necessarily have to be the bad guys, unless that's a training academy for future bad guys, and I don't know, that may be true. Okay, we've already talked about securing your router configuration, ensuring your routers are properly secured, and the config file that defines the router configuration, you want to keep that secure as well, because you don't want some bad guy gaining access to a copy of your, config file on his smartphone or something, and then learning all about how the router's configured. That's bad, MAC limiting. How many different MAC addresses can connect to a different router? So in other words, I've got a particular, I may even have an application that is licensed to only 25 users at a time, and the only way to get to that application is through this particular switch. Well, I may use a MAC limiting to limit the number of addresses that this switch will support to equal my 25 license number. That's an example. MAC filtering, on the other hand, that's where you specify that specific MAC addresses are allowed to get on this network or whatever. So that'll keep the riffraff out. Won't keep the determined hacker out, because he's going to simply
spoof your MAC address, thus getting around that MAC address filtering rule. So, but it's good to keep the riffraff out. Network separation, right? I mean, you could, if you lack imagination and you're lazy, you could just throw everybody onto the same subnet and not worry about it. But that's ridiculous. You don't ever want to do that. You want to break people up into logical subnets with different access permissions and different levels of security. You can't really apply consistent security if everybody's in the same subnet. What you do is you break them into separate subnets. Then it's much easier to apply security policies on a network by network basis. That's what you want to do. So you want to get with the network architect dude, the one that's configuring your IP address plan and kind of making sure that works for your security requirements. And then VLAN management, again, that's like step 2. Network separation / IP address management, that's step 1. VLAN management is step 2. So again, VLANs are good. That allows us to create virtual switches on our real switches. It's generally port-based. In other words, you specify on a port-by-port basis, which VLANs the specific ports belong to. So, if you misconfigure that, it's primarily going to be connectivity problems that you have. But you can wind up having security problems too, if it's too easy to redirect traffic from one VLAN to a particular port where the bad guy's plugged in, kind of a thing. And then the rule of implicit deny in a network environment. Unless you assign permissions, then the user can't do something. You don't need to deny. You just need to not assign permissions. So if there's some user or group that you don't want to have access, don't give them access. Now let me come right on the heels of that and give you the opposite example. Let's say you are a SQL Server administrator, and I know this because I used to be a SQL Server administrator. And normal procedure for SQL Server was to do this. You would create a server logon account for some group that you did not want to have on your system. Let's say you had the undesirables group, and you wanted to keep the undesirables group off of the server. So what the procedure is, you create a login account for the undesirables group. If you remember the undesirables group, that logon applies to you. But the clever thing is next. I've created the logon specifically for the purpose of denying members of the undesirables group access to the server. So you create the logon for this group you don't want to be able to log on. That's counterintuitive, but what you do with it then makes sense. Like, oh, you're creating the logon specifically to keep them out. It's like, well, that makes sense now, So that's kind of counter to the implicit deny rule. It's still a very, very common way to do that, but the sort of more I don't want to say user-friendly, more socially acceptable technique is to use implicit deny, just to keep them out. Just don't assign them any permissions. And then, of course, you're going to have a variety of logs containing a variety of information, and that should be monitored routinely for whatever it is you monitor logs for. There's automated log reading. There's a manual review of logs for you show up, you pour yourself a cup of coffee, put your feet up on the desk, go through your logs and stuff, see what's going on, and then then get into your day. Just a suggestion. Ooh, here's an interesting term: Unified Threat Management. We'll call it UTM for short. That sounds more official. A system that centralizes various security techniques: firewall, anti-malware, intrusion prevention, filtering, content inspection, into a single thing, a single appliance. One of those all-in-one appliance things that does all of those cool things. So again, the concept being, look, man, I'm an administrator. I got to worry about all of these different things, and I got all these different bits of hardware and software that I have to juggle. It's like, oh, what a hassle. Well, this kind of unified threat management solution enables you to kind of cover all of that, all those silly little security concerns, all from one convenient location. So that's the idea there. So these UTM systems are designed to sort of consolidate all of these things, which individually are still very important, but the more individual little things you have to deal with separately, the possibility of letting something slip through the cracks is higher, and it's, there's different things handled by different, and the procedures are different, and it's confusing. And by consolidating all of that goofy stuff into one convenient thing, and that's that you connect to via VPN, you secure connection to the thing, and that makes a lot of sense. So, in all likelihood, you might see a reference to UTM, and it's useful to know that it's a all-in-one appliance for handling a bunch of security procedures. Okay, then we get into our guidelines for applying these procedures. You'll find these in the checklist section on the website, which is useful. And if we go through, look at them, the first bullet makes sense. Manage devices so they're configured according to policies. Duh, that's why you have policies. Document, maintain documentation for all current server configurations. Because in the event of something going south on you and you need to rebuild your environment, well, wouldn't it be nice to know exactly what version of what was running on my server and what service pack? Wouldn't it be nice to know what the correct configuration is? Establish baselines. Again, we described earlier that you may need to kind of do that as an ongoing thing. You may need to reestablish a baseline based on conditions that existed when you took your original baseline. Access control list. Basically at the firewall level or at the router level, you create ACLs that allow and disallow certain classes, categories of traffic from coming and going, along with your implicit deny rules. Keep stuff updated. Only do the stuff that's required on that machine. If this machine is not doing a certain thing, turn that certain thing off, whatever it is. Create and implement a disaster recovery plan. That we cover in our last module of the course. Patches and updates. Anything you don't want to expose to the bad guys, encrypt that stuff. Check your event logs. That's why you have them. And then just ongoing, the buzzword is continuous monitoring. Say it with me, continuous monitoring. Once everything's been implemented, once you pass the implementation step, then you monitor to make sure that everything is working the way it's supposed to be working. And if not, then you need to make adjustments. Hang on, let me check something real quick here. Yeah, I don't want to talk about this before lunch. We'll come back from lunch. We'll talk about wireless networks, or topic E if you're playing the home version. And let's come back at whatever dot 15. 15 minutes after the hour, we'll come back. That gives you 50 minutes for lunch. That should be good. Everybody happy? Life is good? All right then. Elvis has left the building.